Hey guys, welcome to this video. It's one of my favorite videos. I want to talk about the differences between an ACL and a prefix list, which I feel a lot of the people, although they know how it works, they look at the cosmetic differences between an ACL and a prefix list, they forget about the base foundational difference between an ACL and a prefix list. And one of the things that I want to do in this particular video is try to make sure you understand the differences between when to use an ACL, what does an ACL bring to the table, what are the advantages of an ACL versus a prefix list. What does prefix list bring to the table, and where would you want to use a prefix list over an ACL? So let's dive into it. As I said, the way I'm going to do it is I'm going to talk about the characteristics of filtering using an ACL. And these filters with an ACL, you can apply it to any of the routing protocols, whether it's RIP, EIGRP, OSPF, BGP, any of the protocols, you can leverage the ACL capability of doing route filtering. All right, we'll complement that with some examples of using ACLs. We'll do some 007 type of ACLs over here as well. Then we'll take a look at a prefix list. What does a prefix list bring to the table? What are the advantages of using a prefix list over an ACL? And again, complement them with some examples over there as well. So let's get started with that. The first thing, as I said, we're going to take a look at what are the capabilities and the characteristics of an ACL. An ACL it allows you the ability to filter the advertisements, the routes that are coming into my router or going out of my router by taking a look at the network portion of the prefix. Prefix meaning your network. All right. To give you an example of that, let me open up my pen, bring it up over here. I'll open up a blank screen so I can show you an example of that. So let's say I had a router, and this could be done inbound or outbound. I had a router connecting to another router. Keep it simple because my main objective over here is the functionality of the ACL, and this router had 10.1.1.0 /24, 10.1.20 /24, and let's put another network over here, 172.16.10 /24. I have a network connecting router 1 and router 2 to each other, 192.168.1.0, and this is where I want to do the filtering. So let's say I want to do the filtering outbound from router 1. When I send actually before we take a look at the filtering, let's say I'm running a routing protocol, whether it's RIP, EIGRP, OSPF, BGP, doesn't matter. I'm sending the routes across to router 2. When I'm sending the routes across to router 2, the networks that are going across has two elements to it. It has the network element, and I'll put a different color for it, and it has the subnet mask element. So again, I'm going to get 10.1.10, 10.1.20, and 172.16.10 getting propagated to the other side. But when the route's going across, it has the subnet mask along with it. So these are the two elements that you have inside a network that is getting published or advertised to its neighbor. Now, when you use an ACL to filter it, whether you're doing it outbound, or you could apply this ACL if you want to control routes coming into your router on router 2. It doesn't matter. My main objective is to take a look at it from the functionality of the ACL. When you use an ACL to do the filtering, the ACL allows you the ability to take a look at the routes from the perspective of this portion. Now you might say, well, I do use a wildcard mask. Well, the wildcard mask is a matching mask, which basically is telling the ACL which bits in the network portion do you need to match. This portion, I call it the network portion. And this green portion over here is your subnet mask portion. So the ACL, let's say you're saying, I want to permit or deny, let's put an example, 10.1.2.0, and I put an inverse mask or a wildcard mask of 0.0.0.255, I'm basically saying when a prefix, a route is getting propagated over here to router 2, in the network portion, I want to check whatever is a 0 is a match, whatever is a 1, which makes the 255, is an ignore. So basically I'm telling my router which makes it 255 all ones. I'm telling my router in the first octet, I do want to match it. So when the route comes in, if it's got 10 in the first octet, it's got 1 in the second octet, it's got 2 in the third octet, because I'm matching those, match those, ignore the fourth octet. That's what the wildcard mask, what this is called the wildcard mask, is doing. It is not touching anything with the subnet mask. So for example, I could have put the wildcard mask over here to say deny $10.1.0.0.00255.255. What that basically means, any route coming in that has 10 in the first octet because of the 0, 1 in the second octet because of the 0, I don't care what you have in the third or the fourth octet because of the 255s. I need to take this action. The action over here being the deny. And this action could be a deny or a permit. That doesn't matter. So when the route comes in, it checks the 3 networks that are coming in. It checks the first octet is a 10 and both these networks match. The second octet is a 1. That is a match. The rest I don't care about. So both of these incoming networks match my network statement corresponding to my wildcard mask. I'll take this action. I'll deny them. The third one coming in says 10 in the first octet. It's 172. Says no, I'm not going to deny it. It falls to the next action, the next statement, and you need to make sure you put the permit any statement over here. Otherwise, it's going to fall down to that black hole of deny any, and it's going to be blocked as well. All right. So when I say that the ACL just checks the network portion, what I basically mean is that this portion, this thing over here, and this is focusing on just the network portion. It's not even touching the subnet mask. All right, that's one aspect of it. But the thing at the same time that you also need to understand, and that's what an ACL really brings to the table, is the detail that you can do in terms of checking the network portion. It gives you a lot more control over the network portion. What do I mean by that? Let's say I had network, the same statement that I put in. Let's elaborate on that statement. I had the network as 10.1.1.0 and the wildcard mask as 0.0.255.255. What does that really mean? What that basically means is I want to match the first octet as a 0. First octet is a 10 because my wildcard mask is a 0. So whatever is a 0 over here, I need to match it in the incoming network, the one that is getting propagated. And because the second octet of the wildcard mask is also 0, match it. The rest, ignore it. But in reality, I'm not matching it octet by octet. My match over here is bit by bit. What do I mean by bit by bit? So although when you look at it visually, you see an octet matching with a 0. What the router is doing internally is it's converting it to binary. So when you put this in there, it's saying, okay, the network coming in is, let's say, 10.1.1.0 and 10.1.2.0. What it does, it takes this network and matches it against this particular statement over here by looking at, analyzing the wildcard mask, but it's doing it bit by bit. So what it does is it writes the 10 in binary, or it converts the 10 into binary, which is 00001010. If you do the conversion of 10, and if you have the magic table I show in the CCNA class, 32, 16, 8, 4, 2, 1. So if you look at it, I have the last 4 bits that I've played around with. Everything else is a 0. So 8, 4, 2, 1. You have an 8 turned on and a 2 turned on. That's a 10. I'm going to do the rest of them quicker, but I just wanted you guys to see where I'm coming with this. So I have a 10 over here that's coming in a network. This is 10 in the first octet, and I'm going to match it against the 10 over here. So because the 0 is over here, what the 0 basically equates to is not 1 0. It basically is the whole octet is zeros. So it basically is going to put this network over here, and the first octet is also 10. And I am telling it to match each and every bit. How am I telling it to match each and every bit? If you look at the 0, the wildcard, it really is 0, 0, 0, 0, 0, 0, 0, 0. So it's basically telling the router, match the first bit to be 0, the second bit to be 0, third bit to 0, fourth bit should match, which is matching, fifth bit is matching, sixth bit. The 0 means match. But it's a bit by bit type of thing, not a octet by octet thing. So let's take a look at the second one. Does it match? Now in the second one, again, I'm going to convert this into binary, which is simple, 0, 0, 0, 0, 0, 0, 0, 1. And this guy coming in is also 10, 1 over here. So this is also 1. And which bits do I need to match over here? Because my second octet also has all zeros, which basically equates to this number, and 0 means match. I'm going to match it, and they do match. So far in the first 16 bits, I have an equal match. The third octet I have is 1, 1, 1, 1 over here. So it really doesn't matter what I put over here. I'm not even checking because the 1 tells it to ignore. So nothing new over here. Why did I break it into binary? The reason I broke it into binary, you have the ability, if you want to, you can basically say, I want to match the first 4 bits. I don't care about, I want to match the first 5 bits. I don't care about the 6th bit. So I can turn the mask over here to 1, match the 6th, match the 7th, and then match the next 8, ignore the rest. So that would give me a mask over here of 0, 0, 0, 0, 0, 1. 1 over here is 4. So it could be a mask of 4, 255, 255, 255, 2550. So I'm ignoring it. So even if I had a network over here coming in as 0, 0, 0, 0, 1, 1, 1, 0, it would still be okay. How is it okay? Because it still matches the bits that I want to match. I'm matching this one, it's matching. I'm matching this one, I'm matching. Matching, matching. I want it to match, it is matching. This one I needed to ignore. Although there's a mismatch, it really doesn't matter. What is this number? It is 8 plus 4 plus 2, which would have been 14. So even 14.1 would have been denied. So because I'm ignoring it over here, it is not going to be checked. But again, I'm matching this, I'm matching that. So even a 14 network, if I had a network coming in as 14, the 1.0.0, 1.1.0/24, even that would be denied. Why? Because of this matching of this bit. The 4 over here basically means turn this bit on, which is ignoring this bit. So what I'm basically telling it with the mask is I want the first 5 bits to be checked, the 6th bit to be ignored. That's why I turned it on. 1 means ignore. 0, 0, that's where I get the value of 4. 0, 0, 0, 0, 0, 1, 0, 0, which is 4. Match the next, actually, I take that back. It would have been over here, sorry. The 4 would have been over here, 4.0.255.255. So 4 is over here on the first octet. The second one is all zeros, right? So I'm still matching it. So it should be 14.1, and then I don't care about the rest. So I'm matching on the first 2 octets being either a 10 or being a 14. So as long as it's 10 or a 14 in the first octet, 1 in the second octet, the rest I don't care about, it will match. What I'm trying to tell you over here, with an ACL, you do have the ability to check it bit by bit. If you're not comfortable with it, don't worry about it. We do several examples in this particular video regarding that. But the main thing that I wanted you guys to see over here is it doesn't need to be contiguous. You might see some odd numbers in the wildcard mask, which is absolutely okay. If you see a number like this, what do you need to do with the wildcard mask? Convert it into binary. You guys are okay with this. The entire octet needs to be ignored. Entire octet needs to be ignored. Entire octet needs to be checked. How about this odd number? That basically write it into your binary and you'll see 4 is written like this. And because it's written like that, what that basically means, I want in the first octet, because it's in the first octet, to check the first 5 bits, ignore the 6th, and then check the 7th and the 8th bit. So you do have the ability to do that on a bit by bit basis, which gives you a little bit more control on the network portion. And that's what I'm trying to basically say over here in these statements over here. Let's take a look at it now. ACL allows you to filter routes based on the network portion of the prefix. That's what I was talking about over here. I'm only working with, my ACL works specifically only with that. It doesn't touch or check the mask portion. It can be configured inbound or outbound. I could do it from, on that example, router 1 outbound or router 1 inbound. Either one is fine. ACL checks the network portion of the routing updates and filters based on that. We talked about that. It allows you to do a bit-by-bit check on the network portion. This is the power or advantage of an ACL over a prefix list, and we'll take a look at that coming up in some of the examples over here. So now that we have this down, let's take a look at some of the examples. I'm going to start you off with very basic examples and then build it up into some very complex examples as well. So let's take a look at the first example to get your feet wet with an ACL. I have two routers, router 1 and router 2. And what I want to do on router 2, I want router 2 to be configured such that 10.1.2.0 network does not come into router 2 from router 1. Again, assuming that simple topology of what? Router 1 connecting to router 2. So router 2, the administrator of router 2 doesn't want this 10.1.2 network coming in. And how did I do it? Simple ACL, access-list 1, deny, 10.1.2.0, and in the wildcard mask, I'm putting 0000. That means if the first 3 octets, this is easy because it's visually you can check. If the first octet is a 10 of the incoming route, the second octet is a 1, and the third octet is a 10. I don't care what's in the fourth octet. It's ignored because the corresponding value in the wildcard mask is 255, which equates to 1111. 1111 basically means ignore. 1 means an ignore, don't check. So I'm only checking the first 3 octets. Why? Because of the wildcard mask. So if I had networks coming in from router 1, let's say I had 10.1.10, 10.1.20, 10.1.30, it doesn't matter what the mask is because I'm not even checking the mask. 10.1.40, I'm going to take a look at it. If any of the networks have the first octet as a 10, the second octet as a 1, and the third octet as a 2, which is just this one, it will be blocked. All right? So how did I do it? How do I implement it? So access-list deny 10.1.2.0 with a wildcard mask, simple wildcard mask. I'm checking the network portion, permit any. So I'm basically telling it when the route comes in, the first 3 octets, if they match these, take the action, and the action is deny. The rest of the routes, I want to permit them. So once I create the ACL, this is an ACL that will be working off the routing protocol. So if it's a routing protocol, I don't put the ACL on my interface, directly under my interface like E0/0. I don't do an IP access-group command. That would be for data. It checks the actual source and destination IP address of the packet. I'm not worried about that. I'm not concerned about that. My concern is the routes, the networks. So the networks are the data portion, the payload portion of a particular routing protocol, and that's what I'm filtering. I'm not filtering the actual source destination of the packet. That would be a data packet. I'm working off the routing update. So if I'm working on the routing update, I want to do it for the routing protocol. So that ACL needs to be applied under your routing protocol, whether it's EIGRP, whether it's BGP, you could do it for RIP. So you go into your routing protocol. In my case, I went into what? Router EIGRP 111. The command to implement the ACL is by using the command called distribute list number 1, which basically calls the ACL1, saying any route that is allowed or denied by ACL1 coming into the router, into router 2 from this interface should be checked and allowed or blocked based on this ACL. All right, so now if I had router 1, router 2, and let's put router 3 over here as well as an example, and router 2 and router 1, this is the connection. Router 2 has an E01 connected towards R3. Now what I'm doing over here is I'm preventing router 2 to send me the update. Why? I'm applying this distribute list to incoming routes from E00. I did have the ability, if I did want to do that, I could basically say distribute dash list 1 in and leave it like that. So if I put this command in like distribute dash list 1 in, it applies this particular ACL1 to all the interfaces on router 2. So if you want to do that, you also have the capability of doing that. And same thing applies for what? BGP over here. So I gave you an example for EIGRP or BGP that I can apply it. Now with BGP, it's a little more, you could do the distribute dash list command, but BGP gives you one additional capability, which is beyond the other protocols. And what is that? It allows you the ability to apply that distribute list not just on an interface, but to a specific neighbor. How does that matter? How does it different? If you had router 2 over here and it was connected to, let's say, router 1 and router 2 or router 3 over here, if I do this type of thing for BGP, and this is only available in BGP, the neighbor command for applying the distribute list, if I was doing it on E0/0, it would apply to both the neighbors because I'm applying it to all the incoming routes from E0/0. Okay? Now, if I'm doing it based on a neighbor, although both the neighbors are connected on the same interface, my filter is only going to apply to any incoming routes that are coming in, not from E00, but specifically from this neighbor. So BGP gives you an additional capability of doing it per neighbor. If I wanted to do it for all the neighbors on that particular interface, you could technically, rather than doing this, could do this as well. Distribute dash list, same thing that I did for EIGRP. So that capability still exists in BGP. You could still do that, but this is more granular. This allows you the ability to do it per neighbor, which the other one did not. All right. Hopefully you guys are okay with a simple example. I'm basically blocking the 10.1.2 route coming in, that specific route coming in, or anything that has 10.1.2 in the first octet is blocked. Even if I had subnets, for example, I might have multiple subnets of 10.1.2. So I could have 10.1.2 16/28. I could have 10.1.2 32/28, 10.1.2 48, the subnets of this particular network. Now, this particular one is only checking the first 3 octets, and if they match, so I'm checking based on my wildcard, I'm checking 10.1.2, 10.1.2. See this? And just by looking at that, all the 3 networks, because I'm not looking at the last octet at all because of the ignore, I'm going to block all 3 of them. All right? So that's what this wildcard mask allows us the ability to do. It allows us the ability to do it per, per octet. You can do it per interface. In BGP, you could do it per neighbor if you want to apply it. Now, this is a simple example. Now, let's take another look at another example which allows you the ability to check or see the advantage of using an ACL. Now, let's say I had this type of setup where I had a bunch of different networks that started with 2.10.1, and they had a whole bunch of different networks, .1, .2, .3, .4. So, for example, let's say behind router 1, there's a huge set of networks, and all of them belong to 210.1 family. So 1, 2, 3, 4, all the way till 255. So I have a total of 255 networks over here. Now what I want to do over here is on router 2, I want to block in the 210 range, which any network that has 210.1 in the first 2 octets. But in the third octet, I want to block anything that, let's put an odd number. I'll do an odd number first and then we'll do an even number. Anything that has an odd number in there. So what I want to do basically is I want to block any of the odd numbers in the 210 range in the third octet. What do I mean by that? I want to block 210.1.1, 1 is odd, 0/24. I want to block 210.1.3.0/24, 210.1.4.0, not 4, sorry, 5.0/24, 210.1.7.0/24, 210.1.9.0/24, and so on. 11, 13, 15, so on and so forth. So every odd number in that third octet needs to be blocked. All right? How do I go about doing that? You can either write 127 different statements or 127, 128 statements to block them, in there individually, deny this, deny that, or you can leverage the wildcard mask to do it. How do I leverage the wildcard mask to do it? Let's go ahead and take a look at that. Again, I'm going to use a whiteboard over here to set this up. So what I want to do is I want to block anything in the 210.1 in the first 2 octet range in this third octet. So my octet that I'm playing around with is the third octet, anything that has an odd number. And then we'll do an example for an even number as well. So an odd number, what is the characteristic of a number in the third octet that makes it odd? If you remember my chart that I drew a bit ago, 32, 16, 8, 4, 2, and 1. These are the different bit values that I have for the 8 bits in an octet. Now, if you take a look at it, the only bit over here that's an odd bit is my last bit. So if this bit is turned on, mean it is 1, regardless of what I have over here. It doesn't matter, it'll always end up being an odd number. Why? These are all even values. So if you put an odd value at the end, it'll always be an odd value. 1, 3, 5, 7, 9, 11, all of them will have this as a bit turned to 1, bit turned on. So if I want to look at odd numbers, all I got to do is take a look at the last bit in the third octet, because that's the octet that I'm working with. If that's an odd number, guess what? The number will end up being an odd number. So that's all I care about. So the way I would write that in my ACL, so I know my network is going to be 210.1. So in the third octet, I'm checking or looking for the number 1. All right? And the only bit that I care about is this one. The rest of them, I don't really care what's in the first 7 bits. So my wildcard mask is going to be 1, 1, 1, 1, ignore, 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 ignore. I don't care about the first 7. The last one, I'm going to check that. I'm going to check only the last bit. If it's on, meaning it's this value, I'm going to take my action of deny. My wildcard mask then becomes 0, 0. For this one, 1, 1, 1, 1, 1, 1, 1, 0 is 254. And the last octet I don't care about. So my wildcard mask over here is 00254.255, which is basically checking for the last bit to be turned on. If the last bit is turned on, the end value will always be an odd value. Okay? And the action that I want to take, in my case, I want to do a deny. Hopefully you understand that. So the main thing that I wanted you guys to see over here about the ACL, and that goes back to that bit by bit thing that I told you about, is in this particular wildcard mask, I'm telling the router to check the first 8 bits, check the next 8 bits, so the first 16 bits are checked, and then I'm telling it to ignore 7. So the first 16 check, next 7 ignore, and then check this one because of the 0, check the 8th one, which is basically the 24th bit, and then ignore again. Ignore 8. So what you guys are seeing over here is check, ignore, check, ignore. So you can do that throughout the ACL by turning on and off the bits over here to control which bits are you checking. So you can do a lot of different crazy calculations over here to do the wildcard blocks over here, which you could not do, and you'll see that in a prefix list you do not have this type of control over there. So I'm doing a check, ignore, that type of stuff. I'm not doing a flat check, and if it's a mismatch, block it. So along the same lines, I also wanted to show you an odd number. And what is the characteristic of an odd number? Again, if you look at my magic table, 128, 64, 32, 16, 8, 4, 2, 1. Again, this is the only one that determines whether the number is going to be an odd or an even. If this number is a 0, regardless of what's in the first 7, the number will end up being an even number. All right? So if I'm checking for an even number, I'm just checking the same last bit in the third octet, in my case, for what? A 0. So rather than writing for my odds, I wrote 210.1.1 because I was checking for a 1 to take the action, 254, 255. Now, in case of an even number, because the even number will be dictated based on the last bit turned off, so I'm going to check 210.1 because I'm checking the third octet. This number will be a 0.0. The wildcard mask, I'm still checking the same bit. It's just that the value I'm checking for is a 0. So it's going to be 00254 255. So even for an even number, it's still going to be the same mask because it's still determined based on the 24th bit in our case, because I'm checking for the odd even in the third octet. So again, it's the same bit that I'm checking. The difference is, in case of an odd, I'm checking whether the value is 1, because in order for a number to be odd, that value has to be a 1. If I'm checking for even, the last bit has to be turned off, the value of 0, right? And that's what I'm showing you in this example. This is something that you could not do using a prefix list. And when we go to the prefix list, I'll show you that. Over here, this is example 2, the one that we were taking a look at. So I'm blocking what? All the even networks, my network over here, 210.1.00, my mask 00254.255. And if this is for an even number, and if I wanted to check for odd numbers, the only difference would have been the same exact thing, my network, because I'm now checking the third octet for an odd number. The third octet should be a 1, but I'm still, for odd even, the check is the last bit in that octet, which makes it 00254, means ignore the first 7. I don't really care what's on the first 7. The last bit I need to check, and I need to check it against this value, so which is a 0. So that's what the 254 signifies. Ignore the 7, match the last, ignore the last 8 after that. All right, so this is the second example. That's checking odd even. But the good thing about that odd even, the easy part about the odd even was I'm only checking the characteristic based on the last bit in the octet. Let's do something crazier than this. All right, now I'm going to take this example over here and work with it, because this is something that is not that simple to do. And this is not an exact science as well. So sometimes it will work, sometimes it might not work. So you need to take a look at, might not work is you might put a number, it might block more than what you're thinking you're blocking. And I'll explain that as we go through it. So in this particular example, what I want to do, what my objective over here is that I want to take these, I'm receiving these 10 networks from coming into router 2 from router 1. All right, I got a 70, 74, 80, 90, 150, 200, 202, 210, 218, 220. I have 10 different networks coming in. The characteristic is they're all starting with 25.1 in the first 2 octet. All right, the third octet is changing. Now they're all even numbers over here. 70, 90, 202, 220, 74, 150, 210, 80, 200, 218, all even numbers. So I cannot use an odd even. I have a specific requirement that says that I want to block the 74 network, which is this guy over here. I want to block the 90 network, which is this guy over here. I want to block the 202 network, which is over here, and 218 network, which is over here. So these 4 networks need to be blocked. Now, you can always do the 4 networks deny this, deny that, deny that, deny that, the 4 deny statements and permit statement, and it would get it done. But let me show you the power of an ACL where if it works out properly, you have the ability to do it in one line. And in order to do that, you need to follow a certain certain series of steps to get it done. And I've given you those series over here, the stepwise thing in the PPT. And I'll explain that to you. So if I want to do that, if I want to block these 4 networks, I start by writing the octet that I need to play around with. See, 25.1, I know this is common among the 4. Now I want to find something that is common in the third octet. So in order to do that, by looking at the numbers, there's no commonality that I see. So what you need to do is you need to write those 4 numbers that I want to block, specifically the third octet, because I know 25.1 is common between the 4 networks. I'm looking for something common, so I can block it based on that commonality between them. So when you look at these 74, 90, 202, 218, I wrote them in binary over here. All right, so the first step that I need to do over here is a simple step. You take the numbers that are common and write them in binary. Normal binary math that you learned in CCNA. So 74 becomes 0, 1, 0, 0, 1, 0, 1, 0. And just remember, this is 128, that 64, 32, 16, 8, 4, 2, 1. So this is 64 plus 8 plus 2, which is 74. And the next one then is 90, 64 plus 16, which is, 80, 88, 90. 202 is 128 plus 64, which is 192. 192 plus 8 is 200 and 202. The next one is 218, 192, 208, 216, and 218. So all those four networks, I write them in binary. Simple step over here, basic conversion of the third octet, the one that I cannot visually see that they're the same or common. So now that I've done that, the next thing to do, and as I wrote over here for you guys, check the matching bits among the networks and have the wildcard mask check the matching bits. What bits over here are exactly the same in all the four networks? I have my second bit over here, all ones. So that's matching. That means they're all the same. That's common between all four networks. So I can look at that and say, oh, if I want to block these four networks, if I block that particular bit, I am getting my thing done. But there's more to it, because it would leave me with 7 different variables, so it would block a lot more than just those four networks. But if I move forward, you'll see the third bit over here is also the same on all four networks. The first bit has a 0, 0, 1, 1, so it's not the same. 0, 1, 0, 1, not the same. The fifth bit over here, what do you see? All the four networks have the same common, bit value. The sixth one, the seventh one, the eighth one, all of them are common. So if I want to block these four networks, I can just tell my mask to check these bits. And how do I check or tell my wildcard mask to check these bits? The check bit or the match bit, whatever you feel comfortable calling it, is a 0. So I do want to check it because they're common. So that in my wildcard mask will be 0. And if I don't want to check them because they are not common, I will do the ignore bit. Ignore bit is a 1. And looking at it, the first bit in this octet is not common. So I'm going to ignore it because I want to look for common bits. Second bit is common. I want to check it because I want to make sure if it's a common bit, I want to do the deny based on that. The third bit is common. The fourth bit is uncommon between the four networks. The fifth bit is common. Sixth bit is common. Seventh is common. Eighth is common. So 2 bits are uncommon and the rest of the 6 bits are common. But this is the number that becomes your wildcard mask, which tells your router, hey, listen, I want you to check the first and the fourth, I want you to ignore the first and the fourth bit, check the second, the third, the fifth, the sixth, the seventh, and the 8th bit. And hence, if you add the values up, it's 128 plus 16, which is a 144 in the third octet. So I am matching the entire first octet. Why? All four are 25. I'm matching the entire octet in the second octet as well because it's a 1. In the third octet, I'm matching the second, third, fifth, sixth, seventh, and 8th bits, ignoring the first and the fourth bit. And the way I tell the router that is by turning the bits on, ignore them, and that becomes a mask of 144. And the last octet, which is the host octet, I don't really care about it, 255. All right, that's how I come up with the wildcard mask. So you have a wildcard mask of 00144.255. There might be a danger that it might be blocking more than just the 4 networks that you see over here. But in my case, mine is a perfect example in the sense that I have handpicked these 4 networks. Now, if you take a look at it, how many bits are not common? There are 2 bits that are not common. If you have two bits that are not common, that will give you 2 to the power of 2 combinations, which is 4. And all 4 networks are over here. So all the 4 networks that will be blocked based on this mask are there. But just in case, let's say, in my example, I had told you I want to block 74, 90, and 202. Remember that it would have also blocked 218 because of the way the wildcard mask is being presented. So one of the things that I could technically do is I could permit the 218. So I could say permit 25.1.218.0.000.255. So permit that, and then I could do a deny of 25.1. And I'll put the network, I'll show you the network, this guy over here, how I came up with that, 0.0.144.255. That way the specific route is blocked and the other 3 routes are denied, or the specific route is allowed, the other 3 routes are blocked. So if you have not an exact science, this is another way of doing it. I still did it in 2 lines rather than doing it in 4 lines. So still a 50% cut down in the number of ACL entries that I have. All right. So how do I write the network portion? I showed you how to write the wildcard mask portion. Again, to review it, once I write the numbers in binary over here, which number am I writing? The 3rd octet, the network that is not visually common. Once I write that in binary, then you look for common bits. So you cannot see it based on the whole value. So take a look at it from the bits perspective. The 2nd, the 3rd, the 5th, the 6th, the 7th, and the 8th bit are common. Because they're common, I'm going to check them 0, 0, 0, 0, 0, 0, 2nd, 3rd, 5, 6, 7, 8. The ones that are uncommon, I don't want to check them. So I put a 1 over here. And that equates to my wildcard mask of 144 for that octet. Now, what about the network portion? Now, if you take a look at this, I still have this over here. My common bits that I have are this bit, these 2 bits, and these 4 bits at the end. Now, what are the bit values of each one? You have a 64, you have a 32, you have an 8, a 4, a 2, and a 1. But the thing is, out of these 6 bits, the 2nd, the 3rd, 5, 6, 7, and 8, the bits that are on, meaning it's got a 1, all of they're common, so all of the 2nd bits are 1 on this guy, on the 2nd one. The 3rd bit is 0. The 5th bit is all on, so 1. The 6th bit is all 0, so 0. 7th bit is on. 8th bit is 0. So if you add these values, 64 plus 8, 72 plus 2 is 74. And that's where you write this number. So again, how did I get that? Once you write the networks that you want to block in binary, now take a look at the common bits. Again, I'm repeating. This one, common. Write the bit values of the common bits. Again, it's a 2nd bit, which is 64. 3rd bit, which is 32. The 5th bit, which is 8. 4, 2, and 1. Now, out of these 6 bits that are common, that my wildcard mask will tell my router to check which bits are on. The 2nd bit is on. The 3rd bit is off. The 5th bit is on. 6th is off. 7th is on. 8th is off. So it is 64 off, 88, which is on. So 64 plus 8, which is 72. 0 off. 2. Add that because it's on. That becomes 74 and off. So 74. Got it? And that's how I would write this. Access dash list deny 25.1.74.0 00144.255 permit any. Everybody comfortable with it? I know it's a lot. Take a look at it. Do an example. Do this example on your own. See if you can get it. But the main thing that I want you guys to do this, it's not very practical. It's not going to be done a lot in real life, but it shows you the power of an ACL. So what we did over here, if you take a look at the wildcard mask here, I'm telling it to check the first 8, the second 8, in the third octet, I'm telling it to ignore 17, check. Actually, let me put the ignore in a different color. So now I'm 17. Let's do this, 1 second. 1 through 16, that's a 0, 0, check. 17, ignore. 18 and 19, remember this? 18 and 19, check, because of the 0, 0. So I would do 18, 19, check. Again, this bit, ignore, because it's not matching, and that's what I put in my wildcard as well. So 20th, ignore. Then check the next 4. 21, because again 0, 0, 0, 0. 21 through 24, check. And then the last octet which is basically your host octet, 25 through 32, ignore. So check, ignore, and different bits. So first 16 check, 17th one is ignored, 18 and 19 check, 20th is ignored, 21st to 24th is checked, 25th to 32 is ignored. What I'm basically trying to do with an ACL, you can do a bit check anywhere. That's what I was talking about when I meant bit by bit check. This is the power of an ACL. So if you want to do this advanced stuff or advanced matching using an ACL on the network portion, you have the ability to do that using an ACL. You could not do that using a prefix list. That's the advantage of an ACL. All right. And this is again how I would write the ACL, and calling the ACL would be the same way. Let's say I was running BGP or EIGRP. I would just say router, whatever. Let's do EIGRP as an example. 111, and it's just an ACL again. Distribute dash list. 1 in, let's say I want to do it for all the interfaces. All right. So that is what an ACL does. So what does an ACL do? Again, to recap, 2 things that I need you guys to keep in mind when you do the ACL. It only checks what? The network portion. Number 1. And number 2, bit by bit check. So any bit can be checked anywhere. It doesn't have to be contiguous. Those are the 2 characteristics of an ACL. All right, so the ACL is done. Now let's go ahead and take a look at your prefix list. What does prefix list bring to the table? Why would I want to use a prefix list to do the same thing? Let's analyze that. The prefix list allows you the ability to filter by looking in the network portion and the mask portion. So if I had something like this, I could technically take a look at this and take a look at this. So that's what this statement over here is stating. Allows you the ability to filter on the network and the subnet mask portion. For example, if I wanted to block any network that has 10 in the first octet, but with a subnet mask of greater than or equal to 24, 24 and higher, I could write my prefix list like this, where this is telling it in the network portion, I want to check the first 8 bits to be 10. In the subnet mask portion, I want to check this number for what? Not this number, sorry. This is, I want to check the subnet mask portion for 24. So if networks are coming in, so let's say I have a network coming in 10.1.1.0/24, 10.2.0.0/16. Okay, over here is just checking for what? In the network portion, I'm just looking at this. I'm looking for the 8 bits to be 10. Is that true? Both of them are true. So this one is a check, but again, there's an and between the network and the subnet mask portion. Now that I've gotten a check for the network portion, how about the mask? It's going to check the mask against what? This number. The mask, is it greater than or equal to 24? It's not greater than, but it's equal to 24. The E means equal to. So this one is not only matching on the 10, it's also matching on the mask portion. This guy, although it's matching on the network portion, it is not matching on the mask portion because on my prefix list, I've told it should be greater than or equal to 24. It's showing you a 16 over here, which is less than or equal to 24, right? So in that case, this one will be a match. This one will be an ignore. Why? Because it does not match the two elements. So again, when you write a prefix list, you have to write the network portion by using this format. But then it's not done over there. You also need to specify your subnet mask portion by specifying the GE. There's also an option for less than or equal to. So either GE or LE to whatever the number of your mask is. 24. All right. So this is the network. And let me put it in, actually, well, when we do the example, I'll show you this. This is the subnet mask. So when a network comes in, let's say I showed you the two networks, 10.1.0.0 / let's say 16, and I'll reverse it this time around, 10.2.1.0 / 24. And I want to do a deny in my prefix list. The action I want to take is a deny. So what's going to happen over here is when this network comes in, it's going to go through the filter. It's going to say, I want to check in the network portion the first octet as the first octet only because of the 8 over here. This is the network portion match, 10. It matches. Okay, this is good so far. So it's ready to get denied, but wait a minute. I still need to check the mask. And in the mask, let's say I've specified GE 24, and the mask should be greater than or equal to 24. Oops, doesn't match. So it will not do a deny on the 10.1.0 network, although the network matches, the mask portion is not a match. Whereas the second one is 10.2.1.0 / 24. Now, again, let's do the two checks. 10 in the first octet, because of the network portion, it's a match. Why? In the network portion, I'm only checking the first 8 bits to match the 10. It is matching. So the network is done. Now let's check the mask. Mask 24 greater than or equal to 24. Equal to 24. Good enough. So this is also checked. This is also checked. Both are checked. This action will take place. So for a deny to take place, I'm checking by looking at the network portion and the subnet mask portion, which is a good thing. The disadvantage over here is that when you look at the mask, this is basically what your wildcard mask was. From the ACL, this is your wildcard mask in the sense that it's telling the router in the network portion, check these bits. Now over here, I specify a number, which basically means the first X contiguous bits. You cannot say want to match the first 16, ignore the 17th, match the 19th and the 20th. That cannot be done. So in this case, in a prefix list, when you're specifying the network portion, you can only specify the first X number of contiguous bits. So I can only say, okay, in the network portion, the first 8 bits need to match, or the first 16 bits need to match, or the first 20 bits need to match. I cannot say 20 bits match, ignore the rest, match again. I cannot do a bit by bit match. That's what this is specifying over here. The prefix list checks the first X contiguous bits in the network portion. It does not perform a bit by bit check on the network portion. So that does not give you the same control that an ACL would give you on the network portion. But the advantage over here is I can just look at the subnet mask and I can do a check on the subnet mask as well to do the filter. All right. So to drive the prefix list home, let's take a look at some examples for that as well. My first example is I have router 3, router 4 for this example set. I have configured router 3 such that 22.2.2.0 network does not come into router 3 from router 2. So I create a prefix list. The syntax for that, IP prefix list, the name. This is the name that needs to match in the different statements that are part of the same prefix list. I'm saying deny 22.220/24. And notice after that, I did not put the GE or the LE. So what's a mask? If I don't mention any mask over here, the mask basically defaults to this number. It becomes EQ implicitly. You don't see it. It implicitly becomes whatever number you specified over here. So this becomes the mask. Okay? So 22.220 in the network portion, the first 24 bits, if they're matching 22.220, so any network coming in with the first 24 bits being 22.220 and a mask of 24. Because I did not specify the mask, it automatically, implicitly means EQ whatever number you have over here. All right? Now, let me ask you this. If I do this in an ACL, 10.0.0.0/8, because I'm only checking, not 0, because it uses that the wildcard mask. Now, if I write this like this in an ACL, what does it mean? It means, actually, what I want to do is this. What does this mean? This means any network that has a 10 over there in the first octet should be blocked. Okay? I'm not checking the mask. So whether I have 10.1.10, 10.1.20, 10.2.1, 10.2.00/16, anything coming in, it's going to be blocked because I'm only checking the first octet in an ACL, because I'm only checking the network portion. And in the network portion, I'm telling it to check the first octet. If it's a 0, if it's a 10 because of the 0 match, block it. So all of them are blocked. But if I do the same thing in a prefix list, I write a prefix list like 10.0.0.0/8 and leave it. It is looking for a specific network of 10.0.0.0/8 because I did not specify the mask. It says EQ8. So 10.1.10/24 does not match. 10.1.20/24 does not match. 10.2.10 does not match. But I wanted to block all 10 networks. How would I do that then? So don't do it like this. This is incomplete because your don't specify the mask. It basically means the mask is that number 8. So rather than doing that, I can say any mask. And the best way to say any mask is less than equal to 32, means any mask, 32 or less. All right? So in the what I'm saying now is in the network portion, the first octet should be a 10. All right? So in the network portion, the first octet should be a 10, match all three. In the mask portion, less than or equal to 32. Less than or equal to 32. So both are matches. Because now both are matches, I'm going to do a deny for what? All the three networks. You get my point? So when you do this, you're not specifying the subnet mask. If you don't specify the subnet mask, it basically does not take the default. It's a class A network. It doesn't use 8. It uses this number implicitly. So understand that although you did not type it in, think about what happens when you do this. It's blocking based on the mask of 22. So if this network came in, now take a look at it. Is it blocking it? In the first 24 bits, it's 22.220. It's matching. And because I did not specify the mask, it equates to 24. It is equal to 24. So it will do the deny on the 22.220 network, but that specific network is blocking. It's not blocking any other network. Now, the permit. They did not put a permit any statement. This is a very important statement. This is your permit any statement, but let's analyze that. Let's take a look at the permit any statement over here and how they write it in a prefix list. 0000/0. Again, this is just the network portion, means any network. But if I leave it off, what did I tell you happens to your mask? It becomes EQ 0. What network has a mask of 0? The only network that is exactly 000/0 is the default route. So if somebody was sending you a default route like a default information originate, that would get blocked. Anything else, it will not get blocked. So how do I tell it any network and any mask? Well, I told you earlier on, what is the any mask? Less than or equal to 32. So you need to complement it like this. So just remember, permit any is this. Any network, any mask. So don't forget to put in the LE32. This is only going to block the default route if it's getting injected in. LE32 will block all the, or permit all the routes. So this is your permit any or deny any statement that you have. And how do I apply it? In terms of your EIGRP, RIP, those protocols, distribute-list. In the previous example, when I was doing the ACL, I just put the ACL number over here, right? In case you want to apply a prefix list, you need to use this keyword over here called prefix. So distribute-list, prefix, then the name. And the rest of it is the same, inbound and the interface. You could say inbound and leave it off that. That means apply it to all the interfaces, or if you want to do it to a specific interface, E0. You could do that on BGP as well, but BGP does give you this option of prefix list over there. So you're applying this prefix list specific to a neighbor. This is the name of the prefix list and inbound. So this is how you create the ACL. This is how you apply the ACL for EIGRP or for BGP. All right, so it should give you a better idea of a prefix list. Let's do another example over here. Now, configure R3 such that all the 150 networks that have a subnet mask of greater than 20 are blocked from getting propagated. So the first thing I want to focus on, 150.1 that have a subnet mask of 20 are getting blocked. So first thing, before the mask is what in the network portion do I need to match? This network, right? These are the rest of them are subnets. So from the 151 network, I want to block everything. So I would write the prefix list deny 150.1.0.0/16. So in the network portion, I'm matching 150.1. So anything that is part of 150.1, deny it. But what about the mask? Should have a mask greater than 20. And be careful with this, especially if you're taking an exam like a CCI exam. It says greater than 20. That operator is GT, greater than. But the operator that we have access to is not GT, it's GE, greater than or equal to. Greater than 20 is 20, greater than 20 is 21 and above. But we don't have that operator. We don't have greater than 20 operator. We have the GE, which is greater than or equal to. So including that number. So if that's the case, I want to start with 21. I cannot say GE 20 because then it would include 20. I want to start with 21. So I need to say GE 21. And that's why you see this over here. Take a look. 150.1.16. GE 21 and permit the rest. So again, on the 150.1 network, that means the first 16 bits on that network. On that network, any subnets that have what? A mask of 21 or higher should get blocked. Permit the rest. Permit, this is the generic permit any statement. And you apply it. All right. And the last one, last example over here. Again, I'm going to make it a little bit more complicated. Not a very common example, but I want you guys to understand the concept over here. Configure R3 such that all Class B networks are blocked from getting propagated. All Class B networks. Let's analyze that. What characteristic makes a Class A network a Class A network? A Class A network has a rule that says the first bit of the first octet, this bit, is always 0. Just the first bit. And that rule is the one that makes the numbers in a Class A number, first bit is 0. So you can have 0, 1, 1, 1, 1, 1, 1, 1, 1. And if you convert this, it's 1 through 127. The rule, the first bit being 0, is the one that actually sets it up. Similarly, for B, the rule is the first 2 bits have to be 1, 0. First 2 bits. That's a rule for a class B network. So that basically means that in here, when I write them, it'll be 1, 0, and then whatever, whether it's 0, 0, 0, 0, oops. The highest you can have, because the first 2 bits are always 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, which is basically 128. The lowest, the highest is 191. Hence the range 128 through 191. All right? So this is the rule for a B. The rule for a class C is the first 3 bits are 1, 1, 0, which gives you 1, 1, 0, the lowest number being 192, 128 plus 64, the highest number being 1, 1, 0, which is fixed, 1, 1, 1, 1, 1, which is 223. And that's where those numbers come in based on these rules. So now you know what the rule is for an A or a B or a C. The rule for A is the first bit is 0. For B, it's the first 2 bits are 1, 0. The C is 1. The first 3 bits are 1, 1, 0. So if I want to block all class B networks, I'm looking at this rule. So the way I would write that, I'll just use the same place over here, and I'll give you some the entries for A and C as well. So if I want to do deny all class B networks, I would say deny, what is this, 1, 0? If you convert that into binary, I'm only checking the first 2 bits. I really don't care about the other ones, because this makes it a class B network if the first 2 bits are 1, 0. If you look at the binary conversion of it, it's 128. So I'll say 128, because 1, 0 is 128. I don't care about the rest of the bits all the way across. And I'm only checking the first 2 bits. How do I check it? Checking only the 2 bits? 2. And then I can put the mask as any mask. So the first 2 bits, any mask, drop it. The first 2 bits being 128, that makes it a class B network. How about a class A network? What would make a class A network? The first bit being 0. So I would say deny 0. I don't care about the rest. 0 over here. 0 is on the other. And 1, because I'm just checking the first bit to be 0. If the first bit is a 0, it's a class A network. The mask, any mask. You could actually specify GE9 or GE617 for B. And then the third one, deny 110. 11 is 192 /3. Why 3? 110, 3 bits. And the mask. The mask, you can be more specific and put the class A, class B, class C mask, but my main focus was to show you this portion over here. That's a class A, class B, and a class C network. So if now you take a look at this example that I gave you guys over here, I want to block all class B networks. All right, how did I do it? Deny 128, 2. Any mask. Permit the rest. And apply it. And I showed you for A, it would have been 0, 0, 0, 0 /1. Because class A, the first bit is 1. It's a class A network, LE32. For a C, it would have been 192, 0, 0, 0 /3. Why? 110 makes a class C network. And the apply is the same. So now we have taken a look at an ACL versus a prefix list. To review this, again, an ACL. The characteristics. Number 1, checks the network portion. Number 2 is does a bit by bit match. How about a prefix list? Number one, checks the network and subnet mask portion. Two, checks the network based on first X contiguous bits. All right, you cannot do a bit by bit match in a prefix list. Those are the differences between an ACL and a prefix list. All right, so depending on what your requirement is, you can either use an ACL or a prefix list. So now you actually know the internals of how an ACL and a prefix list are different. What are the advantages of an ACL? What are the advantages of a prefix list? Hope you guys enjoyed this video. So let's go on and take a look at how these prefix lists and ACLs work in the different protocols.